All right, what's up, everyone? We're back for another special Polymath Salon with the Machine Perception Cognitive Robotics Lab at FAU, courtesy of Dr. Hahn and Dr. Barenholtz. We also have several students from that lab here today. This time we're going to be having Mr. Dugan Hammock from the Wolfram Institute talk about visualizing 4D geometries and just generally geometry in higher dimensional spaces. He actually gave a good preview of this at the UT Austin Salon that we did I don't know, a couple weeks back at this point with Scott Aronson. He went before him, had a really good presentation. That's up on the YouTube channel if you haven't watched it already. And let's just roll into this. Dr. Hahn, if you want to give yourself a quick intro.
Yeah, thanks, Addy. Super excited to hear this conversation today. Obviously, I've been thinking a lot about AI, and in particular, over the last few years, this idea from high dimensional geometry, that there's something about these very large vectors and high dimensional spaces that we don't understand yet. I like to think in the Middle Ages, when they drew in the corners of the map, here there be monsters. I suspect that there might be some sort of intellectual monsters living in these high dimensional spaces. So I'm really excited to hear what Dugan's going to say today.
All right, Dr. Barenholtz, you want to go next?
Sure. Hey, everybody. Yeah, I'll second that. I mean, what we're seeing now in the space of AI is really just the ability to actually map out trajectories in insanely high dimensional spaces. Turns out that's probably what the brain is in some ways, and our ability to manipulate these things. Well, now we have machines that can kind of do it, but there isn't really, in terms of insight, human insight into what's actually going on. I think we're falling further and further behind in some ways because we're just understanding now that these high dimensional spaces are kind of where the interesting things happen. And so any techniques or abilities that we have to be able to turn these things around outside and point them back into our brain so that we can understand it using our our shared kind of cognitive machinery that we have to understand the visual world, say, seems like a really important kind of pursuit right now.
Awesome. DVZ.
Howdy, my name is Daniel Van Zant. I am a computational neuroscience PhD student under Dr. Elan Barenholtz there. I'm really interested in creating smarter AI to make smarter humans. And I'm actually somewhat of a skeptic on sort of the machine learning field's excitement about conventional Euclidean hyperdimensional spaces. So in math, there's lots and lots of different kinds of spaces, and I think they're useful for lots and lots of things. And so there's lots of really cool things you can do with hyperdimensional spaces, but I don't think it's a Swiss Army knife. And I think there's lots of other very interesting mathematical spaces that could be useful for other kinds of cognitive tasks.
Nicholas, you want to give a quick intro?
Hi, sorry about that. I'm Nicholas. I'm now 12th grader at Vanguard. I am a student researcher at Ekkolapto. Previous research I've done is on ADS-CFT correspondence and also fusion with Bose-Einstein sync condensates.
Nice. Eliade?
Hi there. I'm a perfumer working at QRI, the Qualia Research Institute. I'm just interested in phenomenal objectification and what kinds of homomorphisms can we draw from this field into like electromagnetic topology or graph structures in the brain.
Now, I also we can make the quick announcement that you and Dr. Hahn will be joining for Andres's Qualia Research Institute presentation. I believe that's June 9th, which is going to be a pretty fun time. All three of you will be in together, which is going to be a lot of fun. And then who else? Austin, quick intro.
Hello, my name is Austin. I run open source research and dev organization for computer science, do a lot of math. It's called Alignment Lab AI. And I tend to code and not sleep quite enough.
This sounds like a common occurrence of code over sleep. I've heard this many times. But you know a couple of the people here, right? You've met DVZ and Michael at the Austin thing.
Yeah, it's nice to see you guys again.
Awesome. All right. Well, you'll be meeting more of the crew today. But finally, we're going to have Dugan take it away with a quick intro and then going into his presentation.
Thank you. I'm Dugan. I'm a mathematician and geometer and artist. I work at the Wolfram Institute as a research coordinator. And I'm here to talk to you today about how I compute with and visualize four-dimensional objects, basically embedded in Euclidean four space, to give a flavor. But so there are a couple different methods for visualizing hyper shapes that I've worked with, pioneered. The first one involves convex polytopes. So convex polytopes are defined on a discrete set of vertices in n-dimensional space. So, given a point cloud, how do you go about deciding which vertices are on the facets, for instance, on the outer edges, and which ones define the line segments, for instance. So, if I gave 12 points in space, it's not entirely a priori obvious which facets should be made on this point set. Which of these define the faces. So, like for this one, it's like there are 20 vertices, and it's not obvious until you compute it that those 20 vertices form 12 distinct faces, each with a five-sided polygon. So, as an iterative process, there are a couple different ways to go about computing convex polytopes, especially in 2 dimensions. There's a gift wrapping algorithm, which is most efficient. But here I present a more general algorithm that I discovered that works in arbitrary dimension. So the first step is to try to find an initial set of vertices that encapsulate a volumetric simplex. Here, this is a 2-dimensional example. So you have points scattered on the 2-dimensional plane, and it's up to the algorithm to find out which vertices are connected by exterior edges. The first step is to get a simplex, in this case, a triangle inside, and then for each new vertex that's not in the set of vertices collected already, a new vertex will extend a couple new one or more simplices to it. So you fill the volume essentially with the simplices, obtaining a simplicial complex of the volume of the interior of the shape. So for instance, for a cube, starting out with this tetrahedron and enumerating until all the vertices are filled up, and then there's a simplicial decomposition of the volume of the cube. Here for a dodecahedron, it's a little bit more, there are a lot more simplices bisecting its interior. But once that's in place, you can go ahead and collect the facets of those simplices and collect them by their surface normals, and then group them into faces, and then you're off and running on to having a description of the outer facets. A full face decomposition is obtained thereafter on the set of simplices once that's computed. So a note on these this output here. So for 2-dimensional convex polytopes, it's very simple. You have a set of vertices, and one by one along the outer rim, there are edges connecting adjacent vertices. So here, for instance, there are as many vertices. There are 30 vertices. There are 30 edges. Each edge has 2 vertices in them, and then the whole face is one component containing 30 vertices. For a cube, you have 8 vertices, or 8 zero-dimensional faces. Each zero-dimensional face is just a vertex containing 1 vertex as a set. In the cube, there are 12 one-dimensional faces. A one-dimensional face is just an edge So an edge is a direct link between two vertices, and there are 12 of them here in this case. And in the two-dimensional faces readout, we have 6 quadrilaterals, being the 6 square faces of the cube. For a dodecahedron, we have 12 pentagons, 30 edges, and 20 vertices. Okay, so to obtain slices of convex polytopes, what's needed is to take all the edges of, okay, so let's say we have a 4-dimensional hypershape convex polytope. It's this discrete structure, points, edges, lines, facets, etc. And you want to take a cross section of that with a hyperplane. So the vertices are embedded in 4-dimensional space. A hyperplane segments the vertices into things that are above the plane, below the plane, and then you want to find the vertices that are in line with the hyperplane. So to do that, it's a very simple algorithm. You extract the edges of the polytope. For each edge, you have 2 vertices and a linear functional. That is to say that the hyperplane is defined as a linear as an isosurface of a linear function on Rn. You just have a normal vector and you take a level set using the dot product. So it's easy to sample that function at opposite ends of an edge and then linearly interpolate where the 0 of that function should be given the values of the function on either side. Once the intersection with all the edges is computed, you then take a convex polytope of that subset. This will be a n-1 dimensional section of the hypershape or the polytope. So for a cube, we can take slices parallel to the bottom face, let's say, and we realize the cube as an extrusion of the square in a linear direction perpendicular to itself. If we instead chose to slice the cube at a different angle along a direction which is perpendicular to a body diagonal, that is vertex first going to the equator, we see a different shape. It turns out that you can bisect the cube into 2 halves, each adjacent to each other along a common hexagon. For a dodecahedron, it's a little bit more complicated as a shape, but the equatorial section here is a 10-sided polygon in this orientation. But if we change the orientation to be vertex first, like we did with the cube, then we can realize that there is a hidden hexagon inside the dodecahedron. It surprised me at first, but there's some deep interplay between cubes and dodecahedron, which is pretty fun to think about. Slicing some hypershapes, let's start with the hypercube. So the hypercube has 16 vertices, 32 edges, 24 square faces embedded in there, and then 8 cubic facets. So there's a cube on this side, a cube on that side, and cubes on the remaining coordinate vectors. And here, this is slicing the hypercube along the oblate orientation, getting cubic sections out as the equatorial. That's not the only angle we can slice things at here. If we take a edge first orientation, we get some sort of extruded, tapered hexagonal slice, hexagonal prism, and again, still other orientations. We see some sort of octahedral elements coming into play as equatorial slices of the hypercube. Other hyper four-dimensional polytopes include 24 cell, which is thank you. Yeah, which is made up of 24 octahedral facets. And taking slices of that, we see that there is indeed a equatorial slice, which is a cube octahedron. Let me set this to 0 so that the readout of the slice is indeed the readout which corresponds to a cube octahedron. That is 12 vertices, 24 edges on this thing, and 8 triangles and 6 squares. So if I count the squares on that, that's 6, 8 triangles, it checks out. Very interesting to note that right off equilibrium, it starts to camper its vertices, and this count changes quite a bit. It has, 6 quadrilaterals and 8 6-sided components. In any case, moving along with the examples, this is a 600 cell in orthographic projection, consisting of 120 vertices, 720 edges, 1,200 triangles, and 600 tetrahedral facets. We get some pretty interesting polytopes that don't have specific names coming in as slices here, except for the tetrahedral ends here. So this is a facet first slice orientation. And here we have the vertex first coming in. Near the vertices, there are icosahedrons. And then here, there's some sort of like buckyball in the middle. Okay, so that's a lot of discrete geometry. Working with discrete sets of vertices and the combinatorics of all the determining the facets and the subfacets, as the case may be. For that is sets up a robust, but it's limited. Convex polytopes are limited to these discrete structures, basically. Well, first of all, there's limited to convex shapes in general, which if you wanted to have any sort of concavity, or like a torus has a hole in it, for instance, non-trivial topology, then what's needed is a different way to make hypershapes. So what you can do is what I discovered is it's possible to take a parameterized 3-manifold. That is, you specify in 3 parameter coordinates vertices in 4-dimensional space. And where 3-manifold means you have a shape which is like taffy, taking a 3-dimensional volume and bending it, putting it in 4-dimensional space, curving it. So the technology here, the technique here is to start with a 3-dimensional domain, wrap it into 4-dimensional space, and then that's what this phi is here. You start with a 3-dimensional coordinate domain, map it into 4 space. There's a function on 4 space, namely, like taking a hyperplanar section would indicate a linear functional So you have a function on R4. You can pull that and then a projection to 3 dimensions so you can see it. So the map from the 3-dimensional coordinates chart to R, you can pull back and get a map from R3 to R itself. And since the coordinate domain is 3-dimensional, you have a function defined on the 3-dimensional coordinate grid. So you can use Marching Cubes algorithm to extract isosurface in the parameter space. Once you have that data structure, you then map it back into 4 space and then project it down to 3 space for viewing. All right, so that's kind of technical, but it's let's take a look at what all that means exactly. So for an example of parameterized 2 manifold would be a torus. So here's the parameterization for a torus of like radius, outer radius 6, inner radius of 2, that kind of thing. Set up in the XY plane and then extending in the Z coordinate. So basically this is taking a circle parameterized by theta and bending that circle around a large track parameterized by phi. So taking a cross section here. So here is a view of the parameter space. So this is a 2-dimensional coordinate patch from 0 to 2 pi in both directions, mapping onto the 2-dimensional manifold that is this torus. And in the 3-dimensional space, we have a linear functional defined by this hyperplane, and we can take values of that. And pulling that linear functional of the hyperplane back onto the torus parameter domain gives you this contour plot. And the red here is taking the boundary between the positive and negative values in this parameter space, extracting a curve out of that. Once that curve is modeled in parameter space, it is mapped back into 3 space for viewing. So this connected red curve is this disconnected boundary component here, with the caveat that the left and right and top and bottom boundaries of this domain are connected as periodic boundary conditions. For a hypertorus, it's much the same. You go through the trouble to take the parameterization of a 2 torus and you extend that. So you use the first 2 parameters to parameterize a cross-sectional toroidal element, and then you use the 3rd parameter to bend that around a large track, in this case, the circular track. And so you get a parameterization like this, with some caveats for radius of the big one, the small one, and the other 3rd radius, the 3 radii in this case. So you can take slices of that, and there's a lot of interesting topological changes as a slice moves through the object. So here there are some visual aids to help guide the eye. Essentially, with this rotationally extruded torus, basically there's an outer volume region that contains all the material of the shape. That's indicated by this light mesh. on the outside. Also, since there's a hole in the object being extruded, that void gets pulled around and exposes a volume inside the larger volume, an inner volume, that details where the material is not located. So there's nothing inside the darker gray element here, and everything is inside the outer one. So everything's kind of sandwiched between this encasement and located outside the extrusion of this void. This is already like outside the scope of convex polytopes, mainly because it has a really big hole going through the exterior of it, and connecting through the interior is also a different type of hole. The homology, which you can get lost studying the topology and homology of these things. Really interesting fields of research. With that parameterization in hand, it's also possible to add different amounts of twists to the shape before it is sliced. So here we just went through one axis of slicing and rotated it around to view another one. Here we are adding twists to the shape. So what's happening there is I'm implementing this type of parameterization. Oh, it looks daunting. It's really not so bad. This is a combination of function on top of function, and this is the result algebraically of that. The function I'm implementing is, what, is there a question?
I was gonna, by twisting in the shape in this way, are you changing things topologically, or are you just changing things in sort of the absolute Euclidean sense?
It is a topological change. Basically, to make a Mobius band, you take like a cylinder or a band, and then what would be just you take a cylinder, you cut it, right? And then you add a twist, and then you glue it back again. So this is taking whereas that was like, okay, I have a line segment, and I'm extruding it around, and then before I glue it back to where it started, I'm adding a twist to it. That changes the topology. Here I'm taking a torus, and as I pull it around, I add some twist to it before I glue it back again.
Okay, very interesting. So I didn't mean to throw off your groove. I just had a
question. That's perfectly. All questions welcome. So now with the twisting, there's a lot more singing and dancing that the equatorial slice will do. As I said, that twisting is like reminiscent of Mobius bands. And so far as I added 3 half twists to the object, this slice here is sort of a Mobius band like manifold. Here I'm untwisting it where it was. It's fun to note also that here it's a trifoil. And we untwist along that axis, and then introduce some twists along a different axis, and then they get more taffy coming out of the slices. This shape, I don't know, reminds me of Deep Space Nine a little bit.
So, do we have wormhole aliens here? Or?
Yeah, we got some wormhole aliens. Then untwisted, and then start at the beginning. Okay, so that was yeah, so that was taking this parameterization as this torus is pulled around the blue thing, it tumbles a couple times, and you can tumble it along 3 different directions, axes, and so you have a quite a lot of leeway for different shapes being manifest. All right. Thinking about taking this further a little bit. So how to slice an arbitrarily higher dimensional manifold. So caveat, the convex polytope apparatus I described earlier is extensible to any dimension. And I've worked with polytopes up to dimension 8, including the E8 lattice polytope. And the combinatorics for those get pretty big, but the computer can handle it fairly well, even on optimized code. But for these parameterized manifolds, basically so this technique that I'm using now is using a 3-dimensional coordinate patch. It gets mapped into 4 space. You take a linear functional on that, or any type of functional on 4 space. You can pull that function back to the 3-dimensional parameter space and use marching cubes on that to extract out a 2-dimensional isosurface. Insofar as you can parameterize anything as a coordinate patch, if you had some sort of marching hypercubes algorithm, then you could take whatever isosurfaces you want. The tricky part for that is the combinatorics get pretty wonky for larger and larger dimensional polytopes. So one good way to write that sort of marching hypercubes function would be to have the convex polytope algorithm spit out all the different cases that you would need to enumerate in order to optimize a hypercube, marching hypercube algorithm. With that in place, you could, for instance, take a 4-dimensional manifold, embed that in like 5 or 6 dimensions, and then start taking 3-dimensional slices out of that. But yeah, so with some programming, the potential for this type of thing, this technique is in good shape. There is a third technique which looks at implicitly defined hypershapes. So things of this type of equation where you have like a quadratic in a lot of cases, something where it's measuring the distance of a vertex from some sort of easy to define object. So a hypersphere would be x squared plus y squared plus z squared plus w squared equals 1. Would be the distance from a vertex to a point. You could also ask the question, okay, well, what if I had a circle embedded in space, in 4 space, and you wanted to take all the points that are equidistant from that circle? In 3 dimensions, the points equidistant from a ring would be a torus. And in 4 dimensions, it would be a little bit something else. So for instance, I pulled this off of there's a nice website about hypershapes and computing them in this way. And this is called the Tiger Torus. And it looks like it's some distance between two circles, circle in the XY and the circle in the ZW. Some sort of balance between the ratios of that. So this is involving essentially taking as a parameterized 3 manifold, just a cubic grid of points as a domain in which to call an isosurface function, embedding that 3-dimensional domain in 4 space, and then using one of these quadratic equations to take an isosurface out of that, which is a little bit backwards from what I was doing here with these 3 manifolds. This is taking a very parameterizing, very bendy shape and then intersecting it with a linear functional isosurface. This is taking a linear 3-dimensional parameterization and intersecting that with a quadratic functional. In general, you can take a arbitrarily parameterized 3 manifold and intersect it with an arbitrarily defined isosurface and then compute the result. Beyond that, there's taking sort of metablobs. That is, you know, like in the take a sphere and take another sphere, take the distance functions and add them together, and take the isosurface for that, and you kind of get like a blob covering two vertices and the space between them a little bit. So you can kind of add mud to a pile wherever you want, 1 block at a time, and kind of construct hypershapes that way. So one thing that I made an animation of some years ago in grad school was of this hand-drawn 3 manifold drawn by George K. Francis for a paper by William Thurston. Some exciting intersections. One thing that's fun to do is to take functions on 4 space of 2 complex variables, and such that there's a singularity at the origin, and you can take that isosurface intersection with the hypersphere, get a 2-dimensional manifold out of that, embed it in S3, and then you can stereographically project that back to R3, and you get some very nice looking symmetric type of manifolds that way. So, you know, directions to take this type of stuff is, you know, constructing virtual reality environments in the following way. So, if you imagine what your eye sees or what a camera sees, or specifically in a 3D graphics engine, a camera is defined by a frustum, where a frustum is just projected out, like you take the screen that you're looking at, you project that out into 3 dimensions between a near plane and a far plane, and then you have this 3-dimensional region that clips out what you're looking at in your virtual reality. Usually, this 3-dimensional frustum is embedded in a 3-dimensional ambient world space that you're like moving through, and all you see is what's right in front of you. But this is easily embeddable into 4-dimensional space. Basically, you just keep your 3-dimensional frustum but now you can like tilt up and tilt down in the fourth dimension, and work to maybe navigate around. Maybe have some extra controls controlling your height in the fourth dimension, or your angle of tilt. But imagine, what does a flight simulator look like if you're working in a four-dimensional space? So yeah, so if you have a three-dimensional frustum, then basically you could go to a four-dimensional environment and just keep taking three-dimensional slices out of that ambient geometry. And it's like you're in a dark basement looking with a flashlight, and the flashlight is just probing out a three-dimensional section ahead of you. And you're rooting around this space trying to get to the end of the maze or something. So it'd be fun to like code up mazes like this, or flight simulators, or even driving simulators. What does it mean to drive on a flat road in 4 dimensions, where a flat road is actually a three-dimensional volume? What does it mean to ride a bicycle in 4 dimensions? Because a bicycle in 3 dimensions has a circular wheel attached on a axle that's is basically a linear bar. So you have a linear axle, and around that is rotating a circular wheel. In 4 dimensions, you don't rotate around an axis anymore. You rotate around a fixed plane. That is, you rotate in 2 dimensions, and the other 2 dimensions are fixed. So what does it mean to have not a linear axle anymore, but like a 2-dimensional thing that like is at the center of your wheel? What does your wheel look like? These are experiments that I'm really curious about. So I want to thank you for your time, and open the floor for questions.
All right, awesome. Thank you, Dugan.
Oh, I was trying to hit the clap button.
Oh yeah,
Yes,
Yeah.
yes.
thanks.
No, this
Fantastic.
is great. So I'm curious. DBZ has his hand up. So right now the format is now going to be centered on Dugan and Wilhan. I want to take one question for Dugan. We'll get to Wilhan afterwards, then we'll bring them all together. All right, DBZ, your question.
So I've done some stuff with hyperdimensional fractals before, in particular for turning on Julia sets.
Mhm.
And it looks like you did a lot of work to get to visualize simple shapes in 4 dimensions and 3 dimensions. Whereas when I was working with hyperdimensional fractals, it was like less than 20 lines of code or something, and I had something.
Yeah, it's Ray marching.
Why is it that it's so much simpler? Because in my mind, a fractal is a much more complex, weird shape. So why is it that it's so much simpler to visualize these kinds of weird shapes than it is to visualize simple shapes?
Right. So for the fractal thing, it's not computing the entire description of the surface of the thing. It's just for every pixel that you want to render on the screen, it traces that as a path in 4 dimensions, and every step along that path, it computes the fractal function and tests for does that converge or diverge. And when it gets to a converging thing, it marks that pixel as being incident with the surface of the fractal.
So would it be accurate to say that fractals are much easier to work with because sort of by nature they're generative in a way that other kinds of shapes are not?
Well, it's akin to working with CFDs. Was it where you have a shape, but you define it as a function of how far you are away from it? Like there's a way to calculate that, and the surface is like where that function equals 0. So you're just trying to like trace on a line where a function equals 0 and register like where that point is. So you solve it per line as an optimization, or as a root finding thing. and you're never concerned with where are all the points of the surface located.
That's making some kind of sense to me.
Uh,
This is all very fascinating. This is very cool work.
Glad you appreciate it.
All right, Dr. Hahn, you can take away the spotlight now on the panel.
Awesome. Yeah, thank you. This is such a fascinating talk. I have a few questions that I was thinking about that I wanted to ask you in a broader sense. And I'd love to hear your opinions on it, because
Mhm.
seeing these shapes makes me think of a lot of different things. I'm sure a lot of the listeners the same. And I'm curious about this idea of, you had mentioned a bit, getting intuition and getting experience in these high dimensional spaces. And it looks like the tools that you've built here and these notebooks are essentially giving you, or you have the ability to get intuition in these spaces. And so I wonder if you could comment on that. Do you think that that's happening? Are you getting some kind of intuition that us mere mortals might not have in these high dimensional spaces?
Yeah, a little bit. So, I'm still not at the point where I can close my eyes and like be there. But I am at the point where I can think about, how to stack shapes together and then connect that with like where the material of a hypershape would be. And I can feel around with my eyes closed, so to speak, a little bit more than I can see it. But
Yeah.
There's some intuition building for sure.
Because it almost strikes me as, you've got one of these, Columbus style sailboats, and you're going to new territories. You're going to places where, frankly, very few humans have ever been there.
Yeah.
You had mentioned early on that you consider yourself an artist as well. How do you think that kind of artistic sensibility affects how you approach this kind of science and this kind of math?
Definitely a obsessive desire to like see these new shapes. I just like went through hell to get to this point. A lot of trial and error. And what drove me was I just want to see something big. And I want to see it from 4 dimensions. I want to know what possible shapes there are to make. As a space of design, it's like, okay, sculpture is limited in 3 dimensions due to reasons. What is available in 4 dimensions that's like leaves you more to work with?
Well, that's an interesting take. Do you think that our minds or even life itself lives in 3 dimensions for a particular reason?
I'm very glad it does, because 4 dimensions is very complicated. For instance, you cannot tie your shoes in 4 dimensions.
Right.
Shoelaces are taking and to tie one strand over another, you need one strand, and then you need to have another strand go over it before you can tie a knot. All right. So that's one strand here, and then the space in between makes a 3rd dimension. For 3 dimensions, it's enough to have one strand plus a gap in between, and that adds to 3 dimensions. And higher dimensions, you don't have that luxury. You can always untie knots in 4 dimensions. What you would need to do is you need to tie balloons with strings together instead of
That's what I was
strings
gonna.
with strings.
That's what I was gonna ask. If the regular knot theory kind of dissolves, do we get something else? Right? Do we get something more powerful in a sense?
Yeah, you get something else, and it's called knotted spheres.
Yeah. So it's hard to imagine, like, if we think of kind of the rules of biology, kind of a flatland type scenario, it's hard to imagine biology as we know it existing in 2 or 1 dimension. Do you think, as you're saying with the shoelaces, is that same kind of scenario going to happen with 4? That really it's not easy to live in these other dimensions?
It's likely the case that it's really complicated. You'd have to worry about so much new stuff happening. And
so you had mentioned,
yes,
yeah. I think that's such an interesting that maybe the universe is structured the way it is, or we're in this pocket of whatever we are, or it's kind of the anthropic principle that we're here talking about it precisely because we're in this area where it can kind of support itself.
Mhm.
So I was thinking, you mentioned that you went through hell to get these things working, and I'm curious, do you mean it was just difficult, or is there some other aspect? Because it reminds me of this quote from Roger Penrose, and he said that he had a fever, and that in a brief fit of madness, he briefly described being able to see the fourth dimension.
Oh,
And in not just kind of the biology of knots and things, but do you think our mind sort of has difficulty understanding these other spaces?
I think it has difficulty because it has no grasp of it. I think if it was exposed to it enough, it might gain some traction.
Right.
One of the limiting factors is only having a two-dimensional retina. In 4 dimensions, you would want like a 3-dimensional retina to be able to capture a full volume of information. And to be able to process that would be inexplicable. I mean, it'd be like saying that your retina is as detailed as like an MRI scanner.
Uh-huh.
That you could process all the information of like what's inside of a volume.
Well,
This is-
Dugan, the grounding thing was, remember our previous conversation about like the thought experiment about how you'd come up with fire if you'd never seen anything like it before, right? If you've never seen
Mhm.
anything that's like it before, how do you actually say this is a higher dimension? Like, how would you even come up with it, kind of thing? Because
Well,
right now we're just working with our sort of limited. Like, if someone was just kind of there just measuring
Mhm.
stuff, right? They didn't have any inclination of modern scientific, mathematical, philosophical frameworks. What's there about looking at the rock that tells it, oh, there could be higher spatial dimensions, right?
yeah, I mean, it's a progression of, if you look at the square and the cube, you might be able to know that another extrusion out and you get something different. And you might be able to reason about that using the patterns that you saw from the lower dimensions.
Would you say language is 3-dimensional or 2-dimensional? Because in a sense, written language was always kind of in, at least a lot of formats were in 2 dimensions.
Well, yeah, well, okay, so speaking language is in 1 dimension because you can only
Right.
go out your a linear track on your mouth. If and writing it is sort of linear in a sense. It's a page wrap. Once you get over to the end line, you start a new line and fill out 2 dimensions in a linear way. But at the structure of like syntax is basically you have clauses and then subordinate clauses hanging off of those. And then once you're done saying the subordinate clause, then you get back to the main track and you continue along that thread. So really you have like a tree structure of syntactical meaning tied up in the sentences that are spoken. And so I would say that the dimensionality of language is sort of, as a spoken thing, could be better served in if you wrote sentences and as a graph structure, let's say.
Yeah, super, super amazing. I just had really just kind of one final question I wanted to throw at you. For the last, let's just say, few thousand years, teaching classical geometry has been considered one of the cornerstones of education in terms of creating a well-rounded individual. Do you think that we should or could be teaching this kind of higher dimensional geometry as early as elementary school? And what would that do to kind of our scientific culture? And do you think that would spill out into other areas of human life?
Yeah, well, it's totally doable as far as curriculum is concerned. You could talk about like hypercubes and stuff. Keep it accessible. And then what that would do is that would eliminate some like fear of like, oh no, it's this LLM's in a high dimensional thing. That scares me. You could just take away that obstacle, and you'd have people who would have no trouble delving into these types of things.
That would be fantastic.
Dr. Hahn, do you have anything else you'd want to present on, talk about right now? That's sort of in theme of this.
Just in general, that I'm really excited about. Revolutionizing education, not so much to increase our economy, but just to kind of elevate the cultural consciousness, that we kind of have on the planet. And I think if we imagine taking, scholars from around the world and removing the experience they might have with traditional geometry, I think it would take a lot. It would take a lot away, is what I mean. And so I'm excited to think in the opposite direction. What could we gain as a species by getting intuition in these spaces? I love the idea of using VR to do so. That would be a really killer app for that technology to really be able to jump into those higher dimensional spaces and maybe not go mad like Roger Penrose suggested.
Mm-hmm. Yeah, it shouldn't take a fever dream.
That's right.
Well, something that is interesting, right, is that why is it that we can almost simulate higher dimensional spaces in a lower dimensional space? Like philosophically, why is that the case?
I love it. I mean, I'm trying to think how much a two-dimensional creature would be able to simulate three dimensions. For them, it'd be very difficult, and I don't know how much intuition they get by just looking at a line segment all the time.
Right.
We should be
But
so
there's
lucky
that
that
thing
at
though
least we
about
get.
the fire, right? But like, if you'd have no prior context or inclination and you look at two sticks and rocks or whatever, like there's no way you'd really be like, oh, this is going to turn, we could turn this into a flame or fire or smoke or whatever, right? So yeah, let's just say you are kind of some two-dimensional creature or whatever. Like, how would you even come to the conclusion that there's something outside of that? Right. This goes to the idea of like the unknown unknowns, or like as Dr. Hahn or Barenholtz would say, like the unthinkable thoughts kind of thing, right? It's like what are the things that the blind spots you don't even know that you have? Like there's just the things that you can't even possibly conceive of. And I know this sounds very sort of philosophical, but I think this is actually a very important and practical question to ask, because what we're trying to actually when we're trying to make more capable cognitive systems, whether it's humans, animals, AI, whatever, is that you're sort of asking it to come up with something that it hasn't come up with before in these very sort of novel situations, right? I don't know, just something to think about.
Yeah, the eternal question. Take away all your tools, all your knowledge. How would you think the thoughts that you couldn't think before?
Austin, by the way, you have a lot of cool stuff you're saying in the chat if you want to hop in and talk.
I feel like it's more valuable if I just keep listening to you guys talk.
Well, I know you have very valuable ideas and thoughts, so you're extremely welcome to hop in the discussion. But yeah, like
I don't have a
Nicholas.
question so much as well, where my mind is going with this, kind of predictably. And I'm curious just to
Language?
How'd you can be a mind reader? My God.
He predicted the token.
Turns out we're predictable.
Exactly.
Turns out. So yeah, so of course, and I kind of alluded to this in the before you started, and I've been thinking about it throughout. 4D is tough. Well, what about what about hundreds of thousands of dimensions? What about these giant vectors, these embedding vectors that are how we in the language models and in the brain most likely is how we represent. So when we're doing language, you were thinking sort of in terms of Addy was talking about the actual physical representation of language, and you were kind of thinking about kind of the graph structure of language. But if we think in this space of LLMs, we're really talking about points in very, very high dimensional space, and but they're points, right? Each token is kind of a point in a high dimensional space. So there's embedding that says for this, it's a single high dimensional vector, but it's one point. But where the interesting stuff happens, and this I haven't said the word autoaggression yet, which is a record for me, but it's carving out a path, right? This path dependent sort of a curve in this high dimensional space. And so you can think about sort of, you can definitely think about geometry, in the sense it doesn't have the same meaning of geometry. You can't really define sort of Euclidean distance exactly, although you sort of can. If you
definitely can, and for these vectors, you can
yeah, you can
essentially
certainly define distances in right within vectors.
and angles.
Okay, so
basically
good.
you want to keep things that have embedding vectors that are orthogonal to each other or unrelated to each other, and if they're leaning in the same direction, have a non-trivial dot product, then they have some correlation.
That's for sure, and that's right. That's what the embedding space in some ways is literally what it's doing, is capturing, it's imposing sort of the geometry over in such a way that nearby and orthogonality and proximity and all that are going to carry their sort of semantics. So first of all, I guess just thinking about the space itself, but then also you have the curves, the trajectories through the space. And that's what these models are doing. They're sort of plotting these curves. They're taking the entire path history and saying, okay, given where we've been, where are we going next? And they're forming shapes throughout this. And you, in theory, you could even potentially kind of try to visualize these things. I guess I'm wondering is, what kind of insights might we have from going from from 4D to 3D? And navigating, in the familiar space to navigating an unfamiliar dimensional space, all the way to these much higher dimensional spaces. We can do TS&E. We can dramatically just compress and get rid of most of the dimensions. But turns out, that the high dimensionality is the thing. And so I'm wondering, I don't know to what extent you've thought about, or how I can think about what it would mean to use our cognitive machinery, which is very, very powerful. We can do amazing things in 3 dimensions, and you're kind of trying to shove 4 dimensions in there so that we can do similar things in a somewhat higher dimensional space. Can we think about, is there a way to speculate about what it would mean to go into the much higher dimensional space where these models live, and think about what it means to navigate them, so we could have some insight there?
Mhm.
Right. So, the first thing that comes to mind is sort of taking subspaces of the embedding space to look at things that have the same syntactical meaning, or things that are related, and manifolds, as you said. Right. So the purpose of the high dimensional embedding vectors is basically have all these words in the English language, let's say, and most of them are different from each other, but sometimes they're correlated, and so you try to put them into a space that captures all that correlation information. And in high dimensional spaces, you can, the most amount of orthogonal vectors you can accumulate that are mutually orthogonal, once you hit a limit, you can't fit another orthogonal vector in that arrangement, then you're saying, okay, we're at dimension D. But if you wanted to relax the condition, say like, okay, how many vectors can I get to be mostly pointing orthogonal to each other? And in 2 dimensions, like, you have the most you can get away from 2 orthogonal vectors is like 45 degrees. In 3 dimensions, you can kind of cut a diagonal and get like 60 degrees or whatever from a set of 3 mutually orthogonal vectors. In higher dimensions, you can have a bunch of orthogonal vectors, and you can get pretty close to 90 degrees away from all of them, even though the dimensionality is saturated. And so you can have like hundreds of vectors mostly orthogonal to each other in like a 10-dimensional space without going to like 100 dimensions or whatever. So we can fit like tens of thousands or hundreds of thousands of words in like a vector space of like 1,000, and still have mostly orthogonal, except for where we want to have things leaning towards each other. We can have correlation. And so that's sort of why those high dimensional spaces are useful, because you can keep cramming in unrelated vectors into that space without oversaturating it.
Okay, yeah, right. That's why high dimensions are, but in terms of being able to, I don't know if visualization's even the right word here, but sort of capturing our intuition about navigating through, moving through very high dimensional spaces. Are there tricks that we can borrow maybe from your toolkit in order to think about what it means to go from this word to the next one, right? Traversing those spaces.
Yeah,
And
almost
also,
certainly.
Elon, I think like is the more different, right? Like how much, we're getting this huge shift in properties going from 3 to 4. Well, what if we go to 5, 6, 7, and so on? And then what does that look like on the way to 4,000? Right? Like how many more qualitative kind of changes should we expect as we scale up these dimensions? Or do we quickly get into this weird space where they're kind of similar and we get more, but it's not that different from, let's say, 3 to 4, 2 to 3?
Yeah, I guess it would be interesting to look at because anything like you query an LLM for is like cutting a thread through this space.
Yeah, exactly.
So you want to like cut a hyperplane through like a couple of the nodes that you're interested in talking about at a particular time, and then sort of throw away the rest that's far away from that plane.
Right.
And then just look at subsets essentially.
I like that, Austin. Yeah.
Avram, you have your hand raised.
Yes, can you hear me all right?
Yep, I
Yes.
can hear you.
Right. So two thoughts came to mind in our discussion. One was vague memory of something about fractals, that when you fill the space, where you fractalize the space, you're in effect going to a half dimension. I don't remember more than that. Maybe someone else here remembers it. In other words, the filling space with fractals actually is doing something to sort of invoke another half dimension, so that a three-dimensional space which is fully filled with fractals actually is in some way creating another sort of dimension beyond the three. Does anybody remember anything like that?
Yes, so that's Hausdorff dimension for fractals, such as the Koch curve, or the Sierpinski triangle is a good one. The Sierpinski triangle, right, has all these triangles cut out of it in a symmetric way, and if you double each of its axes, right, so you scale it up by 2, a factor of 2 in each dimension on a 2-dimensional plane, the area of it fractals out, right? So you've iterated it once doing that. So you've taken all these triangles and moved them to other triangles. So you've doubled each axis. You should typically it should be a factor of 4 on the area, but for this fractal, it's a factor of 3. So it's has a 3 square. When you're, it has a scaling law different than r squared. That's just an example of a Hausdorff dimension that's non-integer for these fractals. So it is interesting to think about spaces which are just above 3, but not quite. It's like 3 plus a little bit of wrinkliness that gets it on its way to 4, but doesn't quite get there. It's a very interesting sort of question to think about what types of spaces those would be.
Do you think our brain is trying to do that sort of thing? You mentioned the wrinkly. You mentioned like it's 3D but wrinkly. That makes me think of the brain.
Yeah, sure. Yeah, our brains are trying to curl up into a nice Hausdorff dimension.
Right.
Before I go into some ideas about the geometry of biology, Avram, do you have any more questions at all?
Yeah, the second thought that I wanted to share was, in some sense, at least metaphorically, I'm not quite ready to say literally, the idea to me of inspiration, it sort of reminds me as if we were seeing something in a higher dimension, but we don't know where it's coming from. It just pops into existence. The same way when you're in 2 dimensions, a finger can poke in and pop out of nowhere. To me, some kinds of insights are, at least metaphorically, coming from a higher dimension that we can't visualize so well because of our limited 3-dimensional capability, but somehow we know that there's some truth there. And science certainly is very familiar with the idea of visualizations representing certain kinds of insights that scientists have then found to actually be true. Hercule's chemistry vision is just one of them. And I'm thinking that, in fact, we are already approaching a 4th dimension. We just don't know it. And we don't have a name for it. And we don't know how to deal with it. And I think the kinds of tools that Dugan has come up with could actually be useful in exercising that capability, which I personally believe is already there.
Yeah, I'll agree with you that I think that there is a capability to gain intuition about these things, and it's there, just needs to be exercised.
And you have just provided us with a beautiful exercise tool. Thank you.
You're most welcome.
Any other questions? Everyone?
Enough
Good.
for now. Yeah,
All
I
right,
will have
cool.
some, I'm sure. After
Yeah,
I
and
go
you should
check out.
You
You
should
can
check
always
out
reach out to
Dugan's
me.
work. Yeah, and reach out to him independently as well. Dugan's very smart.
To Dugan.
Yeah.
I've already done that at the sandbox.
Oh yeah. Oh yes. Good. So I should have your contact info. I remember you.
Awesome.
Thank
Cool.
you.
Yeah, thank you. Yeah, so I guess one of the things before also I start, does anybody else have any other questions right now?
I was going to just chime in with a comment to point people towards other really interesting 4-dimensional research that I talk about every time it gets brought up. There's a psychology study where they wanted to see if humans could gain a well enough intuition for 4 dimensions to effectively navigate 4-dimensional mazes that they could see sort of 3-dimensional slices of. And the answer is yes. So we're having all these questions about, can the brain even get a good intuition for 4 dimensions? Can we reason about it? And the empirical answer, at least well enough to navigate through a maze, even if you aren't conscious of the process, it seems to be yes, which I think is really fascinating.
That's awesome.
Yeah, I've been thinking a lot about sort of the geometry of agential systems, whether that's different animals, bacteria, humans, AI, whatever. If you sort of think about, there's a lot of various ideas on the internet about the geometry of things like the heart and the brain, but why are they formed in the way that they are, right? And is there something about the geometry of like encephalization and the wrinkles in the brain that are suggestive of something else? It looks like, maybe Dr. Hahn has something to say about this.
No, I just agree with you. I think that, in a sense, all of biology is trying to create these either higher dimensional or lower dimensional manifolds for which it sort of operates in. So the brain is clearly folded and organized the way it is for a lot of reasons. There's a lot of evolutionary pressure on it, and I don't think we know yet why. I think we have some ideas from network science, but I think we need to think about this kind of higher dimensional or pseudo higher dimensional. Is it, like you mentioned with the hypercube? Well, the brain can wire up as a hypercube, no problem. Is it then acting like a 4-dimensional object?
I mean, is it not doing that now?
That's what I mean. Yeah.
I mean, weren't there some results some years ago about taking a topological measurement of how the brain is connected, and they're saying there's some sort of 7-dimensional manifold coming out of there, and you can the dimensionality of how things are topologically topologically connected can be such that, you can have 8 neurons, you can connect them, link them, like an octagon in a chain, and that'll be like a 2-dimensional type of connectivity between those 8 neurons. But you could also link them up as you would a cube, and you get something 3-dimensional based on the connectivity. Now, the actual placement of those actual neurons in space doesn't have to be the same dimension in which they're implicitly connected to each other. So it is possible to embed, a hypercube related graph in neurons in your brain.
So that makes me think of kind of Lovecraftian kind of monsters in a sense, right? So if we can create these higher dimensional structures in our brain just by wiring it up, does that mean some virtualized hyperdimensional critter might be crawling around there?
Certainly possible.
Yeah, something I was thinking about. So I'm wondering how many of you have ever heard of this thing called casino meditation. This is me coming in with the cognitive enhancement biohacking perspective on things, but it's basically sort of this thing where you can train to have a very strong after image such that you can then kind of control it at will. And there's not will as in William Hahn, but will as in will, right? And there's lots of ways you can kind of train this. Sometimes they involve sort of staring at a dim flame or some kind of high contrast image on a screen. But one of the things, if you train it this good enough, is you start to become very sort of aware. Like if you're looking at your hand right now and you kind of move it side to side, you're very aware of that kind of drag. Like you're actually seeing that kind of motion blur. And if you do it enough, the motion blur actually stays. Almost like, how if you've ever gone on like a really low shutter speed on a camera and you've held like a flashlight up and you've tried to like draw symbols, it literally starts to look like that. I mean, you can actually kind of get some of that to a degree by doing this. And one thing I would think about was just the general geometry of motion. Like when, if I had like a skateboard, I'm watching a skateboarder do tricks and I'm looking at the lines that the skateboarder is doing when it's doing a tray flip or a kick flip or whatever, that ends up looking like a shape. If all of those movements are stored in one frame of time, in like an image that looks like a shape, that looks like geometry, it actually looks like some higher dimensional geometry, especially in the way that sometimes, if you can kind of visualize it in your head right now, the way a board is spinning and going back in a slightly different direction than where it came before, and it can do all this kind of stuff. And I would think about the spatial representations of motion. Like what do, an object that's moving, if it's all looked at one kind of lapse of time, what does it look like? Because one of the things that I've always thought a lot about was, I did this thing many years ago. I don't know if this was middle school or something, but I made this presentation for something, and I taken like, I don't know, you can get like time lapses of like the ocean and nature and the earth or whatever. And like, basically if you speed it up enough, it starts to look like a living thing. Like just, water, tree, rocks moving, all that kind of stuff, clouds, all of that. If you speed that up enough, that literally starts to look like an organism growing and adapting. And there's something interesting about the way you're compressing that time. And if you compress time so much such that it looks like a single frame of an object where everything kind of freezes, right? You start to see these very interesting shapes out of things that move, right? So like literally, if you wanted to have fun with this, you can, Nicholas, I'll get to your question in a second. If you literally right now you have a decent kind of mirrorless DSLR camera or whatever, you turn down the shutter speed a bunch, and you have like the flashlight on your phone, or you have some object, and if you try to move that around, it's going to start to look like a literal physical shape, an object that you can pick up and hold. And I'm very interested in the way we experience motion and change, because this might just be one way of experiencing motion. To another kind of mind, they may be experiencing motion as something more like a geometrical freeze frame, if that makes sense. Am I communicating this well, Dugan? You're gonna have to.
Oh yeah, I mean, the first thing that comes to mind is split scan photography.
Right.
And a digital equivalent of that is sort of, you have a movie, a two-dimensional stack of images that makes a stack of two-dimensional images makes a three-dimensional stack of pixels. Your bottom frame is your first frame, and then you stack the frames, and if you tilt your viewing slice, essentially, that you're tilting it such that, let's say, the left hand of your image comes at a time which is sooner than the right side, and then you view your movie like that, slanted, then you can get very strange effects interplaying with motion and time. And looking at those effects and for two-dimensional movies is one thing. You can also extrapolate that. Say, like, I have a scene, a three-dimensional movie, and you stack those things and then tilt that, and you get a replaying of a three-dimensional movie, but and time is warped.
Here's maybe another way I can phrase that. Will, you wanted to hop in real quick?
Oh, no, go ahead.
No, I was gonna say, you know, one of the things I think about, I'm very interested in filmmaking, storytelling, narratives, whatever. And it's like each time you're watching a movie, you're getting one slice off the whole of the shape. You're seeing one side. It's like, you know, when we look at a cube, we don't actually see the entirety of the cube. We only sort of see slices of it. And it's only until we rotate it and we do these transformations that we can then stitch together this continuity. But the point is that you're seeing different slices and perspectives until then you can line it up and call it, you know, the shape of a cube. And, you know, narratives in general, whether they're narratives in real life that happen just in our day-to-day lives of, you know, what happens in our day, to, you know, all kinds of different movies and things, is like, it would be very interesting if you could geometrically map the narratives of different kinds of films and stories, especially the ones that are less linear, like a Memento or Tenet kind of thing. Like, what type of shape would they look like when stitched together? Right? Because there is this, you know, I think there's some people that have said they have kinds of like geometrical synesthesia things for phenomena like that. But I do think there's, beyond just sort of geometry as a field in of itself, the act of looking at different slices of things and then stitching together that continuity, right? And how language and coordination play a role in that. Because, you know, even at one of the other salons, Dugan, and I actually think DBZ and all were there for this as well. But, you know, there's an interesting thing that happens where it's like, let's say you're seeing one side of a shape, I'm seeing the other side of a shape, but we have to find a way to keep our limited perspectives on things where we are. We can't move, but we have to find a way to understand what the whole shape is talking about, because you're only seeing one side and I'm only seeing another side. And we have to sort of adapt some kind of language-like system that lets us coordinate and stitch together our perspectives, right? So this sort of is that famous blind man and the elephant story. You know, much could be said about this kind of idea. But the other thing also, sort of sidetrack, was I like cars a lot. I like cars quite a bit. And I think about, you know, like the rotary engine, like the Wankel engine versus like a normal piston engine, is that those are different kinds of literal shapes that you're using to create this kind of engine computer that gets the car to do all these kinds of behaviors and things. And I'd be very interested in if we were able to explore the different geometries of engines for vehicles, right? I think electric vehicles are very cool. I think choosing more diverse fuel sources are very cool. But I think it's also cool to see, like, what's the absolute most we can get out of a gasoline or diesel engine, just out of principle, right? So there's certain benefits you could say about having a rotary engine, because it is sort of this curved triangular shape. I think there's a very specific term people in geometry use to refer to that shape. DVZ, you know what I'm talking about, right? On cars? Yeah, like the Mazda RX-7. Yeah, rotary engines
awful
versus
fuel efficiency, but they're really cool.
Well, right. Well, so what would you say are the reasons besides the cool engine sound that somebody would prefer a rotary engine?
Rotary engines, you can go from sort of a small amount of horsepower to a large amount of horsepower. So normally people talk about horsepower as like sort of a car's maximum capability, but horsepower is also a relative thing where you have so much horsepower at any given time. And rotary engines allow you to go from a small to a large amount of horsepower in a really short amount of time. And this is really good for things like drifting. But I've met a guy and I've gotten to talk to his mechanics team who drifts with a rotary engine. And if you do that, you get 18 gallons to the mile, they told me. But but it's really, it can do things that a standard piston engine can't do without exploding. So you could do it with a standard piston engine, but you might not make it all the way there.
So in my effort to one day become like Ken Block or some kind of rally driver or something at some point, is I would love to kind of build an engine that gets you the benefits of the piston engine, but then also the benefits of the rotary engine or some kind of hybrid between them. And I'm very interested in the way that sort of the mechanics of different shapes work when they're put together, because even the idea of gearing is geometry. They're a kind of shape, and they have certain relationships and ways of aligning and communicating with each other, right? I mean, that's basically the entire vehicle industry, right? And even many other industries as well, obviously, but at least in my obsession about cars is that like that a car is basically working off of those parts. Like, yeah, sure, there's the controlled explosion of the fuel, but there's also everything else that's turning it into this thing that lets you steer, move around, accelerate, brake, do all these kinds of things, right?
It's absolutely fascinating, great hard work that you're doing, and I didn't get to talk about the thing that Will brought up, but I do want to discuss that because it's something we had, I think, intimated a little bit first time I heard about this work, which is about the capacities for people to learn radically different representations of of space, and with how cognitively closed are we, I guess, is the question, and to what extent we could possibly develop intuitions for this kind of navigation through higher dimensional spaces. That's something, it's too far back in the conversation, and I unfortunately do have to jump off, but something I'm very deeply interested in, and would even like to talk about potentially doing some experimental work on that front, thinking about how we could actually do this in VR, and lock people in for a while, give them tap, as you were discussing. Can you find a certain point? Can you navigate to a certain location? You've been through the map, now you have to get back. Can you find a shorter path? These kinds of things, to see if people can really get intuitions about how to navigate these spaces. So I did want to just bring that up as a point of strong interest. And so but I don't want to I don't want to short wire the conversation where it is right now.
No, it's totally, I'm with you 100%. We should stay in contact, follow up, and then
let's please do that. Summer is a good time to maybe just kickstart something like that.
Absolutely.
Okay, thank you.
Are we seeing a potential research collaboration?
Sorry?
Are we seeing a potential research collaboration?
That's the hope.
Oh, yeah.
Elan from the MPCR, Dugan from the Wolfram. By the way, Elan, do you have a potential special announcement you want to make to people here?
Well,
Little teaser.
It's a little early. I don't. It's we're having preliminary conversations.
Awesome. All right, we'll see you, Elan.
Thanks for the plug, Addy. I appreciate it.
Of course.
Thanks
See you,
and
Elan.
all thanks to you, Addy. Really, very
Thank
much.
you.
So. Thanks for making these kinds of things happen. They're awesome.
Thank you. I couldn't be possible without you. Bye, Elan. All right. Yeah. Anyway, so back to the conversation about drifting or cars, but I'm very interested in I am very interested in the sort of geometry of motion, right? So if you took something that was moving and you sort of, the way you're looking at that motion, you kept the shutter speed of the camera very low and it all looks like one object. Why does motion have that kind of representation of the shape that it does? And again, this I think Austin,
persistence of
yes.
vision, right?
Yes. Oh, here, hold on. Austin has his hand raised. Go for it.
So I think a good allegory that may have literally nothing to do with the situation in reality could be very similar to this frustrum culling view slide right here, as far as parallax is concerned. At least this is how we had been interpreting some stuff that we were using for like representation research, that we were just getting like in non-linear amount of learning to compression through. It turned out it was because we were accidentally causing a geometric behavior that was compressing in a directional manner, and it looked spatially a lot like this image here. All the things on the axis that we were compressing in were just sort of further away and less concise, or less detailed. at least information theoretically.
Mhm.
It's a lot of analogies. Sorry, like if I can't show Python, I'm not so good on describing these things.
Well, yeah. So you were talking about you're trying to probe this high dimensional space. You had it collapse to 3, and what the data points you're looking at kind of fell into a Frustrum like scenario. Is that what you're?
So we had it was a complex setup that we were doing a different experiment on, and I had described an algorithm to one of my researchers who misunderstood it and implemented something that was different, that was doing like a sort of pairwise summation in a directional fashion. And so they were basically taking a plane of in-bit values that we were using as like a token representation and computing into like integers, like base 16 integers or something, and summing them by the bit values, so that as you went further from the left or the right, there were more values summed in, basically. So the values on the right-hand side were basically the original values, and then they were continuously summed together going to the left-hand side. And it was resulting in these strings that were just like very much smaller than what we started with because they were just getting added together. But the models were learning it as fast as they were when it was the full information without any kind of summation, and we couldn't figure out why. And so we had to go through this whole multi-month long thing to get to the bottom of it. And it turned out we were making Cayley graphs.
Oh, wow.
Yeah, it was.
Oh,
like
I love those.
From group
like
theory.
And to interpolate something at another step that just like reduced the information space dramatically. We didn't realize it.
Did you
That's
see
really
the
interesting.
cage graph comment I made in the chat? Cage graphs are kind of like Cayley graphs, but finite. Like they're essentially like they have this tree structure everywhere, where every vertex has the same degree, but they are like, instead of having like leaves which aren't connected to anything, it's connects like back to itself. So it's this like closed structure essentially.
Dude, that here, I'm gonna grab one of the visualizations from when we did that, and then I'll post a link here because it looks very similar to this.
Okay. They're like extremely hyperbolic, and I think that neural networks made with them might have like some interesting effects. Like signals can like propagate across the entire network very well with like minimal connections.
So it feels like a tree. It feels like you go to like a vertex and it has some nodes that go down from it, and you go to one of those and you keep going like that. But in a tree, you never go back to where you came from. But here it could be cyclic.
Yeah, precisely.
Okay. Yeah, that's interesting.
By the way, I think Dr. Hahn has to run in a second. Was there anything you wanted to say before you headed out?
I just wanted to give the opportunity to thank our speaker. I think this was a fantastic discussion. Love to continue it soon and hear from the audience, and then also plan out some of these experiments. I think that would be super fun.
Absolutely.
So thank you again, sir.
I'm into it.
Fantastic dialogue. All right, I got to
Perfect.
run. Y'all,
Thanks for having me.
please continue.
I will.
Thanks,
take
Thanks,
care.
y'all.
Bye, Dr. Hahn.
Thanks, everybody.
Yeah. I don't know. So what are some of like the more eccentric applications for these things? I mean, there's a handful of things that are kind of more on the practical side, right? But then there's also things about like, I guess sort of the motion thing I was saying earlier. I think that's sort of a more weirder perspective. One of the things, I mean, what are sort of the use cases you're thinking that this is good for right now? Like in current modern, math and physics and all that, besides the sort of artistic value of how beautiful these things can be.
Right. So like utilitarian wise, for me, it was working with convex polytopes was necessary for me to do work in calculating mathematical tilings and quasicrystals.
Oh, I just had a side thought about something. So what do you know how like on a digital audio workspace like a DAW, when you're making music or something and you're trying to program sounds, is you can have 2 or 3 dimensions that represent the sound waves, right? And the sort of shape and texture of them. What does that look like in higher dimensions?
Like analysis of a waveform.
Yeah, like if you go on like an FL Studio, Ableton Live, whatever, and you pull up
Yeah.
a thing, sort of see the waveform. But then also if you're designing, like I think this is on like Serum or something, is you can sort of see the thing in 3 dimensions, right? Like so it looks like how it would in like an old CRT TV or whatever. And what do those sounds look like when represented in higher dimensional spaces?
Well, I like looking at spectrograms, which gives
Right.
you a frequency and intensity over time plot of the different overtones that are going on. What that doesn't give you, so it gives you intensity as a function of color, and then time as a function of left and right, and then the y-axis as frequency. And it doesn't give you any information on phase of the overtones. You can sort of maybe get a different coordinate for that. If that is helpful to the spectrogram analysis, I'm not sure. But I would be, for instance, I'm interested in how dynamic digital signaling processes extract out human voice from background noise, for instance, or how they isolate vocals from guitar tracks and drum tracks. I bet that's a medium to high dimensional process that could benefit from this, hyperdimensional visualization techniques.
As far as the audio things go, you would have to figure out because audio, if you're looking at it in 2 or 3 dimensions, you're looking at sort of several different frequency domains at once that pertain to the particular audio. So you'd have to think about what frequency domains you're adding in there that the extra dimensions apply to. And then I had another thought, but it would derail the great conversation happening now.
Yeah, let me wrap up my thought and I'll make sure you get yours in. But I think what I was going to talk about was perception, going back on the topic of the sort of the perception of things, right? About perception of higher dimensional spaces. If there was just some kid, all right, that comes and looks at any of the shapes that you've kind of laid out in your presentation, like would they have any reason to believe this is talking about like a higher spatial dimension, even if they already know about 1D, 2D, and 3D, right? And I wonder how many things around us right now look like they're they look like they're kind of 3D, but they could be more functionally interpreted as being in some kind of higher spatial dimension. And I think of this especially, when I think of things like knots, right? So in a much older salon, I think you were there for this. I think it was Jesse, DBZ, Michael, I think some returning crew, right? And I would think of a knot, right? If you just were to look at this for the first time in 2D, like a photo of a kind of knot, you wouldn't, or something where there's a string that's going over another string, like a physical string or a rope, right? There's something covering another background of it, right? And so there's something I used to think about where it's like, if I had a tangled rope or string, like a cable for something, right? Like what way could I look at it that gives me the impression that I'm looking at this in 2D, and as soon as I see this in 3D, then I realize how I can untangle it. Because I think it's going to be much easier to understand how to untangle, a wrapped up wire if you can understand it intuitively in 3 dimensions. And part of what you're doing is you're trying to fill in the gap of the missing information. Like if I were to just draw, if I were to go on a piece of paper right now and draw, the sort of highlight of, a cable that's all tangled up, that'll look like one big shape. That doesn't have any other defining characteristics that tell you there's a rear to it. There's something extending from it. If I'm explaining this right. And there's something I think interesting about the cognition and perception process that's inferential about information of shapes that's missing to the perceiver, right? And so the point with this is saying that how many of the things that we think are 3D in our current world may actually be 4-dimensional or higher. By the way, the question is for Dugan, but if anybody else
I'm trying to think, it's an interesting question. Is there anything in our 3-dimensional world that could actually be somehow 4-dimensional?
Oh yeah, that's basically everything. If you believe in Kluser-Klein theory, that is.
Yeah, so I mean, mapping out trajectories in 3 dimensions over time. So, for instance, if you're mapping out orbital mechanics, saying a probe to Saturn or something, and you have to hop by all these planets on the way to get like gravity kicks to get the probe out there. Then you're threading this needle through, like, okay, you take the solar system, plot its movement over time, and you're trying to like angle up a trajectory of, oh, I need to hit this planet at this time up here in the future, starting from this point in the past. You get these curves going, and then you're trying to do a trajectory through this space. Inherently, the problem is like 4-dimensional.
Nicholas, you had a question.
Well, I had one, but you actually talked about it earlier, Addy specifically. It was visualizing smaller dimension, lower dimensional items and higher dimensional things, and I was just trying to relate it to how some people could see, like if you look at a 2D graph, you'll see a 3D graph instead. But I did want to provide a possible answer to Dugan. So knot theory, there's specifically the higher dimensional knot theory, which relates to it. Not sure if that'd be an actual answer to the question, since it's kind of not related as much, but I think that'd be an interesting avenue to go down with high dimensional knot theory.
So like knotted spheres, for instance?
Pretty much, yeah. I can link a paper, actually.
Oh, sure.
I mean, technically our universe is like 4D. So if you were to imagine just like a knot sitting there, it's actually just you can imagine it being extruded in the time dimension. So it's actually kind of like a knotted 2D surface in a way.
It is a bit of a long paper, but it'd take a bit too
Algebraic surgery in dimension 2. Oh, codimension 2. Yeah. Cool. Looks like a lot of homology. Thank you.
Yeah. Oh, actually, okay, here we go. This is what I was thinking about. You should talk to people from Quality Research Institute, Dugan.
Okay.
I think a lot of your sort of work in geometry might be useful. So Eliade, who was there earlier, was actually also, he also brought this up. I think there'd be some interesting overlaps there. I had something I was going to say, and I forgot it. DVZ or Michael, if you had any other, or Austin, if you had any questions, comments, or Jordan, who also just joined, if you have any questions.
Honestly, I'm afraid if I start talking, I just won't stop.
That's fine. We're all like that. You're good. Keep going.
No, I think this is all very interesting. It's really hard to see where everything stops being correlated, right? Like it's like very strongly, there is a cluster of very useful things happening computationally, like right on this domain of like projected geometric Euclidean surfaces and like Platonic solids. I hesitate to articulate that in a way that gives detail without needing a 2-hour exposition. But I signal that it is cool.
I believe it.
So anyways.
I'm really sad.
Go ahead, Michael.
Oh, sorry, I'm really sad that I wasn't really able to attend most of this salon. It sounds like a lot of interesting stuff was discussed. I also heard like fractal stuff getting brought up a couple of times. I don't really know what was said.
Oh, that was a point about fractional dimensions.
Yeah, and we're recording this, and this will be up on the channel at some point. I'm letting the Scott Aronson video marinate a bit, so I want it to get to 10K, and then I'll call it a day. I'm hoping it'll reach that in the next few days. But I know this is great. We should probably wrap up soon because it's almost 4. But thank you everyone for joining as usual. I know we actually have a couple guests who are from the Austin Salon. So there's Austin, Jordan, Michael Ostroff was there, DVZ, Dugan. I also may have been there at the Austin Salon, but that's debatable. I could be in multiple places at once sometimes. But yeah, no, I think this is very fun. And you know, I always do try to bring in the kind of cognition, biology perspective to things, because I feel like looking at the geometry of perception in biology is a very interesting thing, right? So I had a long talk with someone the other day about the material properties of agency. I know Michael Levin has spoken about this a bit, but I would think, you know, how can you get a material to do something, right? And it's not that you're literally telling it to, you're not necessarily explicitly commanding it to do something, right? When you teach somebody, I think sometimes when it comes to teaching people, sometimes it's better to set the conditions in the environment, in the ecosystem, rather than tell them to do something, right? Because if you just tell them to do something, that sort of just trains the ability to kind of do what you're told, kind of thing, right? And to sort of follow this very, you know, explicitly given instruction, rather than being able to come to conclusions and form your own goals and ideas of things more independently and autonomously. And you know, one of the things I think about is we have a lot of, you know, we'll say that the body is a kind of computer or whatever. There's all these things, right? And you know, there's something interesting where if you think about something like skin, right? Now think about the spatial properties of something like skin, the geometrical properties, why it's the molecules have the shapes that they do and the way that they change and adapt over time or whatever, right? But why is it that I think you could almost phrase the property of a material as almost it's the geometry of its particles, the types of shapes and bonds and connections that they make, right? Which is kind of interesting to think about. You know, geometry and chemistry, geochemistry, I don't know, something like that, right? Geometrical chemistry, I don't know. But something that's interesting, right? Is I would think about, you know, if you're trying to build a system that's able to constantly change, you don't want something that's super rigid and hard. You want something that's sort of semi-hard, semi-soft, something kind of in between, right? And something I was talking about with a philosopher just earlier today actually was on, you know, how do you get a computer to sort of self-heal and generate? Like, how do you get, for instance, you have the software element of like a PCB, right? The thing that's happening in the circuitry of a PCB or a GPU or whatever, right? And it's changing aspects of itself in the software angle, right? But then how do you actually change the physical aspects of that thing? Can you have some kind of material that a GPU-like system is made of where it can physically change itself? Like when you learn a skill and when your brain responds to things, it's physically changing. When you're exercising, your heart is physically changing. Your lungs are physically very, very measurably changing. What does a sort of growing computer look like? All right, this talks about that mineral computing thing I think the three of us spoke about a couple of weeks back. So Nicholas saying relating to biocomputers that are currently being made. Well, yeah, I think it's you know, I had a conversation with someone about that, you know, oh, biology is all circuits. What's sort of the difference between biology and computers? Well, I think it's the way that it's remodeling itself, right? I think there's something, I do often wonder that, you know, even if life evolved in very, very different ways, and we already have an insane amount of diversity of it just on Earth that we know of, is that what are the other ways you could get a biological, you can get the benefits of modern computers, but in a biological system, right? And, you know, if you look at a lot of different, you know, things like extremophiles in life or whatever, like there's some really crazy ways these things have kind of somehow come together, right? And I do feel like when I think of materials and I go, you know, to a lower scale, if I zoom in on it, it looks like they're just shapes. Cells have a shape. Why are cells circular or circular-like? I mean, at least animal cells are sort of more circular and spherical, but why is it that not something else, right? If you look at sort of the geometry and the fractal-like patterns of the way the nervous system and you know, vasculature system is, why is it the way that it is? Right, we have no problem talking about the way that we have, you know, the equivalent of vessels in a nervous system in a computer or in something like an engine. Well, how does it all tie together? Right, so I have this other thing I want to do another salon on at some point about engines as computers, and maybe I'll get some mechanic or automotive engineer to hop on in the discussion. But I think in a lot of ways, when you're talking about a shape, you're almost talking about how different things connect to each other. right? And it's a
Well,
shape
yeah,
when
I
there's
mean, you
a
can
level
look
of
at difference
yeah,
engines.
exactly. Yes, symmetry gives in built-in quality checks. This is an interesting topic we should touch on for another time. But yeah, any last questions, by the way?
Do you have a Discord server?
Yeah, you're on it, right?
No.
Oh, okay. Here, I'll send it to you when we're done. Yeah. Oh, for anybody who's on here, I think everyone is on the Discord. But if you aren't, I'll just put the link in the chat real quick.
I'm gonna
So,
funnel
right.
so many giant brains in there that it's gonna explode.
Yeah.
Hey, there's some cool people in the Ekkolapto Discord. There's
No way there isn't.
Yeah.
As far as
there's
I'm
some-
aware, you only know cool people.
Hey, thank you. Hey, man, I appreciate that. Hey, that's all of these guys right here. That's Dugan, Michael, DVZ, all everyone here. All these guys are very smart. Hold on, okay, cool. All right, a couple things I want to make some announcements for. So I actually just did this in the Discord. So yeah, so there's a couple big things that are happening this summer with Ekkolapto. There was just this one with Dugan. Tomorrow, Dr. Hahn is joining us again with AI researcher Peter Voss, who's in Austin. I think some of you met him. They're going to be talking about the principles of generally intelligent systems, like AGI. And then also tomorrow later on, shortly after that, we're followed by Paul Hahn from Yale, who'll be presenting on his project of human skin augmentation. Both of these presentations and salons are online. Very, very cool stuff. Saturday, Willem Nielsen from the Wolfram Institute will be presenting on his essay with Stephen Wolfram on what can we learn about engineering and innovation from half a century of the game of life of cellular automata, which is basically this principle of meta-engineering. What are the computational properties, the computational properties of innovation, right? In terms of things like cellular automata. And then a super big one is on Monday on 6/9, a special presentation by Andres from Qualia Research Institute. He's going to be talking about the screens of consciousness, and it'll be followed by a panel with Andres himself. Eliade from QRI, who was also just on the, who was just, yes, Nicholas, yes. Who was just on the panel, and then also Dr. Wilhan will be joining in on that panel. After that, some of you may know Stephen Gupka from the Center for the Future Mind and Rice University will be presenting on the philosophy of human-computer interactions. But then also a very special thing that's sort of a little more of a new thing. So I'm putting together a Ekkolapto cognitive hackathon retreat. It's probably going to be just 1 weekend long, probably in South Florida. It'll be this summer. It's going to be an intensive weekend retreat focused on enhancing human cognitive capabilities and engineering phenomenology. So basically, think of it like a very technical meditation retreat, but also mixed in with some crazy engineering and philosophy. All right, so it'll be very similar to these kinds of salon discussions, but we're actually going to literally be trying to modify our minds at the same time. So, Dr. Hahn likes to talk about this musical color language called Sorisol. I have the olfactory language, ways of sort of changing the way you literally experience information and think of concepts and all that kind of stuff. Spots are very limited, but you guys on the salon and then the Discord is the first to hear about this. Let's bring quality. Yeah, we should Andres and Eliade, they'd be great. And hey, if this thing goes really well, if this thing in South Florida goes really well, I could also do one when I come to Austin, because I am planning to be back for a string of Texas events, Ekkolapto Texas events, probably later part of June into early August. Later part of July into early August, I believe. I think we'll have one similar to the last one we did with Aronson. I think we're going to do one that's a little more longevity and biology focused. We'll have a mix of things, but yes, that's it for now. Hopefully, yes, if it's as good as it sounds, I'm never coming back. Yeah, well, good thing you're at least not too far from the UT campus, but at least compared to us in Florida. But anyways, all right, let's wrap it up. Thank you everyone again for joining. Dugan, real quick, where can everybody find you online? Just a reminder.
And, follow me on Twitter. A lot of the code that I've been demonstrating here is available on the Wolfram community page. Connect with me there.
And you're on X/Twitter, right?
And I'm on X, yes, Twitter.
All right, real quick. Let's see. Everyone else, anybody else who wants to chip in about where people can find you, DVZ?
www.danielvanzant.com. All of my stuff that's a hub for everything.
Ostroff?
I have my YouTube channel and Substack by the names of Perpetual Science. So you can see what I'm doing there.
Scott?
Yeah, I don't have anything to offer you guys other than real estate skills and business skills, but I'm enjoying learning from you.
Fair enough. I appreciate your incredible open-mindedness and energy to join these kinds of things. All right, Austin, where can people find you?
Alignmentlab.ai is my website. Twitter is alignment_lab. I post a lot of free stuff on Twitter. If you like just mostly useless code, unless you really like doing deep nerd things.
Nicholas? Oh, you have a Substack now, right?
I do have a Substack. I haven't posted in a little bit, but I'm planning on posting something soon. Passing Thoughts, it's called. Other than that, just LinkedIn and Twitter, where I just repost stuff from Substack. So
Awesome. And then Jordan, where can people find you?
It's mostly on X right now, also tag teaming with Alignment, but my handle is Jordan W.A. Parker on Twitter, X.
Perfect. Awesome. All right. Thank you, everyone. I will see you all around for the next one. Hopefully, we'll be joining for the ones in the next couple of days. We've gotten quite a few signups actually for the ones tomorrow, which is kind of cool. But yes, thank you, each and every one of you, again, for joining. I know I probably should say it more, but thank you. None of this would be possible without each and every single one of you. Have a wonderful day.
Thank you, Addy.
All right, see you guys. Peace.
Bye.
Bye. All right, good job today, Dugan. Good stuff.
Thanks.
Let's make